I'm really happy to have these panelists here today. I'm going to turn over to them in a second, but I wanted to just give a little bit of sort of context setting. So at UChicago, arguably the primary mode of carbon dioxide removal that we research is ocean alkalinity enhancement. That's why we're talking about it today. So it's one of the few CDR methods that I would say is inarguably scalable in terms of the potential if you ignore cost. So we're talking about the idea of increasing the storage of carbon in the ocean, which is already by far the dominant reservoir of carbon in the superficial Earth, and doing this by adding alkalinity, which is sort of the net charge balance. It's a concept that people takes a minute to get around, but basically changing the charge balance in the ocean by adding positive ions in a way that interacts with CO2 to store it as bicarbonate and sort of hide it from the atmosphere, and that induces an air-sea CO2 flux. So that's basically the sort of chemical basics of what we're doing. The question is how you actually add that alkalinity. So you can do this through electrochemical methods, you can do this through adding rocks or minerals, or you can do this by adding fast-reacting sort of processed minerals, inorganic calcium species, which is called lime. And then there are a bunch of different research questions that we want to ask, but the one that we're going to be focusing on today is mostly, does it work? So how effective is it and what the controls on that are? And then very related questions from the scientific perspective of, if you've added some alkalinity to seawater, how do you actually know, or how can you measure how much CO2 drawdown you've done? So that's kind of measuring, reporting, and verification question. So you're not all here to listen to me, you're here to listen to the panelists. So I'll say, I'll shut up now. And I thought I would just start by asking each of our panelists if you could each tell us a bit about how your work connects to the question of how much atmospheric CO2 is added alkalinity actually removes. And in doing that, maybe you could introduce yourselves a little bit.
So let me let you guys just take this in for a second. I'll just explain what this is, and it'll give some context about the role that our organization plays in this space. So this is a simulation using a three-dimensional hydrodynamic model. It's called the Regional Ocean Modeling System, ROMS, that is coupled to a biogeochemical model. And it's simulating the release of an alkalinity plumes from a theoretical set of wastewater treatment plants in the Salish Sea. So we're looking here at an area around Vancouver and Port Angeles and Washington, and how that then moves locally within the Salish Sea and then spreads out into the Pacific, right? And this is a plume which is, I would say, about 3 to 4 orders of magnitude less than the natural background alkalinity that would be in the ocean. So a reminder just for folks, because this came up a lot in the previous seminar we had, which is these are very, very small perturbations to the background in the ocean. Okay. But a couple of things just wanted to highlight here as you look at this, which is one, is that when you put alkalinity in the ocean, it moves. It's really obvious when you see the simulations of it. It's not always obvious when we're just talking to a general audience, actually how quickly the dispersal of any of these signals we put in the ocean happens. This is over a 3-month period as simulated. If you wait a couple of years, maybe out to 5 years, you will see that these signals actually can spread across the entire basins of oceans, right? And so this problem that we have, which is asking these questions about how much CO2 is actually taken up, where is it taken up, and the total amount of how much is it taken up are ones where we actually have to use numerical models that are regional scale and out to global scale in order to answer those types of questions. And so these types of modeling systems, they are tools that have existed within the academic and research space for decades. This is not something that we need to develop from scratch right now. Our organization came into being a couple of years ago for the purpose of recognizing that there was a need within the idea of a trustworthy and scalable OAE, or direct ocean removal industry, that these research tools were made more available to companies, researchers, people who are making decision makers, so that there was sort of a arsenal of these types of modeling tools that could be used and improved for this particular resource. And so that's what our organization does. We are oceanographic modelers. We build what we call the computational infrastructure that can be used by the industry and researchers as it grows and scales. We are what's called we can think of us as a nonprofit, technical nonprofit, R&D nonprofit. And we are philanthropically funded, so nonprofit, and then also we are what's called a focused research organization. So it's an organization which is meant to be finite term, so the development of these computational resources that can go out into the world, and then over time we will transform into another type of organization, is the thought there. So that's the role that our organization plays. That was a lot. Was anything I missed there?
Not good. Yeah.
Okay. We pass it on.
Great. So I'm Michel. I'm a scientist at the Woods Hole Oceanographic Institution. So we're located in Woods Hole, Massachusetts, and we're also a nonprofit research organization. We do share a PhD program with MIT. So we have graduate students in our program that are students at MIT. And so I'm in the Department of Applied Ocean Physics and Engineering and part of a group called Loch Ness, which is locking away carbon in the Northeast Shelf and Slope. And because we are a multidisciplinary oceanographic institution, we have a group that came together to work on this project from engineering, which is my background. We have marine chemists, we have physical oceanographers, we have modelers, we have experimentalists, we have technology developers. So we brought this team together to work on ocean alkalinity enhancement. And I came from it from the perspective as my lab does a lot of development of carbon sensors, so measuring CO2 dissolved in organic carbon, methane. How do we develop the technologies to do that? And how do we do it autonomously? So my lab's role has really been looking at it from how do we do the engineering and how do we actually make those measurements and how do we move forward into a place where we're not just doing ship-based measurements. And so we were funded through philanthropy to put this project together. And we did a dispersal in 2025 in the Gulf of Maine off the Wilkinson Basin. And what you're seeing here is kind of a schematic of what we have done. We did a smaller trial in 2024, which was just a dye release. And then we shifted in 2025 to a different location where we did sodium hydroxide for our dispersal. And we were EPA permitted to do this project. And what you're seeing in this picture is basically we used a ship to do the dispersal. So we released alkalinity and the dye. And then we pretty much threw at it every kind of technology that we had available, made pretty much every kind of measurement you could make, did everything from satellite-based to collecting water samples to having robotic platforms out there. And really the goal was to see, what can we measure? How do we make those measurements? And based on this, we hope to move forward with not having to have 3 ships out there and figuring out how to do kind of these measurements autonomously as we move forward.
Great. I'm Noah Planavsky. I'm a professor of Earth and Planetary Sciences at Yale University. So I work on a wide range of different types of geochemical carbon dioxide removal, interested in how we can generate alkalinity to remove carbon in a wide range of pathways. So we have a lab group that makes measurements and does biogeochemical modeling. A lot of work is focused in agricultural settings, where the goal is really to transport alkalinity and have long-term storage in the ocean. But we also do work in basic ocean modeling and do a lot of work of thinking about how we can tie into existing practices and existing industries. So I consider myself a biogeochemist, and a joke is that it's only a matter of time before a biogeochemist becomes interested in wastewater treatment. The rates are just incredible. So I do a lot of work in wastewater treatment, trying to introduce alkalinity and also think about ways in which we can have natural sources of alkalinity, modify natural ecosystems through processes like restoration to generate alkalinity and store that permanently in the ocean.
Great. Thanks, everybody. So I'm just going to jump into the kind of main question we're here to talk about today. So I'd like to ask each of you, so if you imagine OAE happening at the gigaton scale, what do you think is the sort of rate limiting process, biggest scientific uncertainty or unknown that we need to answer, or that would be a problem?
Yeah, am I starting? Great. Well, I think one of the things that when we think about scientific uncertainty, one of the things I think we need to be really careful about is not moving into this idea of a process works or not. Without question, we can remove gigatons of carbon through ocean alkaline enhancement. That is not up for scientific debate. The real question is, how cost effective is this going to be? And that's a question where how can we constrain the inefficiencies in certain areas to gather whether this process will be cost competitive versus other pathways. So I think when we're thinking about it from gigaton scale, we're asking really, is this something that will be more cost competitive relative to other pathways for what is going to be the actual limited amount of money we can put into that? And to me, a lot of that is going to be from the scientific side. What are the areas where this is best suited? And then trying to ask that is this something that also benefits the communities where the deployments are based out of, where the people actually moving these forward are based out of. So I think for whenever we have the key scientific questions, the other aspect to tie to that is, what are the scientific uncertainties that affect cost, and how is the local communities that it affects going to take and benefit from any process in that area?
I think it's an interesting question to try to prioritize. And I'm not going to fall into the trap of prioritizing what are the biggest uncertainties, but just to reflect on what instead we see from my vantage point. So I agree with Noah that I think a lot of these questions that are actually going to be gatekeeping are very much about things like supply chain and cost, and they're very these practical questions. Very often, they're not the ones that we as scientists are first thinking about. Maybe we're first thinking about things like what I showed, which is like, how does alkalinity move in the ocean? So it's just pointing out that there are actually uncertainties all along this chain of scientific knowledge about how we're going to do things at cost. I think there's a lot of uncertainties that are going to come up. Maybe you'll talk about them around what are the deployment strategies, and whether or not we can actually effectively deliver alkalinity into the ocean. And then once alkalinity is delivered into the ocean, we have our whole host of uncertainties that we have about how that alkalinity actually turns into carbon removal out into in a coastal environment or out into the ocean. Because I work in that space, I think a lot about those levels of uncertainty, although I won't say that they are the most important. But just to name a few, just so people kind of get a flavor for what these uncertainties are. The simulations that I showed you were at around a 600 meter resolution. That means the model is run at around 600 meters is the smallest scale within the model, right? In order to run these models out for multiple decades, which is what you need to do to fully understand the carbon removal, we typically have to run models at a coarser and coarser resolution to be able to afford that, right? And so we have this problem within the oceanographic modeling space, which is, we call it the sort of the multi-scale problem, which is that there are important processes that are happening at scales which we do not resolve in our 3D hydrodynamic models. Okay. And so there are these intrinsic uncertainties that exist because we have these computational limitations on how costly running these simulations are. And so I think some of the more interesting work on that side of it, which is not about deployment or about kinetics, is about these questions of, as we move to a finer and finer resolution of our modeling systems, do we start to understand the processes of uptake differently? And that could come out through, do we have actually faster air-sea gas equilibration because we are resolving more of the atmospheric winds that are moving across and driving some of that air-sea gas exchange? Do we have different pathways of subduction, which would move alkalinity away from the surface where it can draw carbon, and so it makes it less efficient? Does that resolution actually just change the pathways and our understanding of where the alkalinity goes? So big uncertainties that I would say still exist within the space of this, like where does it transport and where does the actual carbon uptake take place within the numerical modeling context. I think the good news in that case is that we actually, as a community, have a lot of the tools on hand to ask and answer those types of questions. And a lot of it is just a matter of having sort of the computational time and infrastructure to ask them.
Okay, so I want to answer this slightly differently. Is that I think so? There's these huge questions on like logistics and how we would do this, and some of that I think boils down to an engineering and economic analysis, which in some ways I feel like we can solve. But I think some of these open questions about like what's happening in the ocean and what is the scientific harder part. And I say that for someone who's worked in oceanography for a long time, that the ocean is very difficult to work in. And there's so many parameters that change. I mean, a storm comes through and something happens, or the temperature rises and something happens. So there's so many parameters in the ocean that influence how things are happening that, we can do the modeling, right? But we don't know all the parameters necessarily exactly what's happening. So I think understanding the observational part and integrating up with the modeling will hopefully answer some of these questions. But I think there's still a lot of uncertainty because the ocean is difficult to work in and it's constantly changing.
Yeah.
So I want to ask a question that kind of touches on something that Noah and Alicia both pointed out. So I think yesterday we had a strong sense, I think, in the conversations we were hearing that sort of SRM is the controversial topic and CDR is its like uncontroversial little cousin. A lot of us who work on OAE might have been surprised by that because right now when we're talking about doing gigaton scale OAE, we're often thinking about doing that in the high seas or the open ocean, where there really is not a clear policy framework for how to do this. All of the OAE that actually happens in practice today is done in coastal environments, which we've seen already are dynamic and difficult to predict in a lot of ways. I guess I wanted to ask all of you in terms of, what it means for large-scale OAE if we are not able to do this in the high seas or the open ocean. So if deployment is restricted to exclusive economic zones where there are sort of clear policy frameworks to do this today, what constraints does that have on CO2 removal? How do you pick a site that's favorable or unfavorable? How do you think about the kind of community engagement sides of that? How do you determine whether it's favorable for the local communities?
I could start on that because we've sort of addressed this a bit with our project, is that we did this dye dispersal in 2024 and then, in 2023. And in 2024, we were going to go back to the same site to do the alkalinity enhancement. We ended up not being able to do it because the way the U.S. oceanographic ships work is that there's a bit of a prioritization process, and we were chartering a ship, and we got bumped off the schedule because when a ship broke. But in that process, we ended up moving our field site for 2025 to a different site. And part of that was that we had conversations with local communities, especially with fishermen. And there was a lot of question on like what were we doing? Was it safe? And there was a lot of misinformation. And so we actually hadn't originally planned to do a lot of outreach to local communities. And it became actually a huge part of our project was meeting with people, explaining the science at a level that people could understand. People were very worried. We've gone back to some of those groups since then, and we've even had people say, oh, we didn't understand. Now we understand what you were doing. We actually also when we did our dispersal, we brought out several people from different fisheries groups and from the state of Massachusetts, Department of, I think it was Natural Resources. And so we tried to engage the community, and that really helped for people to have buy-in into our program. So I think that idea of community outreach and making sure that people feel comfortable is a really critical part of this going forward.
Yeah. Just sort of add to that around, so you heard two themes there, community and engagement, and then also permitting questions. And I think that a couple of things, because you said limiting, whether or not it's actually limiting. And I think the one thing about permitting is that the good news about OAE in coastal environments is that there are permitting structures that actually can apply as already stands. We have the NPDES and the MPRSA. So these are under the EPA. And so the good news there is that there is protection in some ways already existing. So this idea that we're going to have OAE releases that are sort of exceeding what we already understand as important thresholds is an unrealistic fear that people have right now. I think the bigger issue that comes up around permitting, as I've understood it and talked to other companies and has been reflected to me, is that there are, one, a lot of times regulators and permitters just don't have the resources or the fluency in these new technologies. So it's actually quite difficult, even if they want to do really good regulation, for them to have the bandwidth to sort of spin up on some of these processes. So the actual getting of a permit, while in theory is completely possible, is one which can be exceptionally expensive, as you have to work over long periods of time with a regulator, right? So that's an important piece of it. I'll add in that the community engagement, the role that we have had at Seaworthy actually in community engagement has come about actually through things like creating simulations like I showed you earlier. That one was actually done as part of a community engagement exercise that was done in Port Angeles, Washington. And it was about actually exploring the way that the community dialogue potentially changes when you put in front of them what it would look like to have a plausible local simulation, okay? And indeed, my experience with that community engagement is that, one, there was a really, really big shift in the type of dialogue that happened in a community forum when people were actually looking at plausible realizations of what this could mean in their backyard. I don't know how much this is done in SRM. I sort of suspect maybe not much yet, but I think it's a really powerful way that we need to think about things like the modeling systems that we have. We build them for quantification, but what we actually see is that they have a very, very high utility for supporting things like permitting decisions and education for people who are already very educated on the topic, actually. And then also as a tool for communicating with communities and allowing them to have something to push against and ask questions about in terms of what it means for their particular coastlines.
Can I just add one thing? That the reason the community outreach is connected to the permitting, at least in our process, when we permitted through the EPA, there was an open comment period. So that's why it was important for people to understand what we were doing so that we wouldn't end up with a lot of negative comments.
Yeah, but agree on all those. I think I'll take it in a slightly different direction. Maybe actually going back to last night. David made a joke last night that I quite like, so that modification of current aviation practices can be a gateway drug for SRM. And I've been making that joke a lot for thinking about alkalinity processes. Introduction of alkalinity through existing practices can allow and pave the way for broader scale ocean alkaline enhancement. So for wastewater treatment plants, an essential aspect of keeping wastewater treatment plants functioning is adding alkalinity. We have bacteria that remove pollution from wastewater treatment plants. Nobody argues that we shouldn't be doing that. That is a unquestionable net good. So introducing the idea that we have alkalinity modification at scale through processes that are essential. I think mangroves also, as I introduced before, another way to have that. Mangroves generate alkalinity. That and mangrove restoration and protection is something that has really widespread support. So making sure that we are not only talking about alkalinity and ocean alkaline enhancement as dumping chemicals is, I think, something that is really important. And to go more directly back to the question, I think why that's important is we lose a lot if we are limited to exclusive economic zones. And the way that I think about that most directly is if we lose shipping channels and we lose the ability to tie to existing shipping, that is something that I think is going to be a serious step back in how quickly we can scale ocean alkaline enhancement.
Thanks. I guess I'm wondering if you all think of coastal OAE as a gateway drug to open ocean OAE too, or if you think of this as something different.
Hopefully David is okay noting the SRM junk joke.
So I want to switch gears a little bit. I guess I want to ask also about measurement, reporting, and verification, because this is another major science question. This is arguably the place that science has one of the larger roles in the question of ocean alkalinity enhancement. Anna, you talked earlier about the sort of integration of observations and models, and Alicia, you showed a simulation that makes it very clear that alkalinity is dispersed very quickly. The air-sea gas exchange sort of equilibration timescale in the ocean is very slow for CO2, by the way. So it takes much longer for alkalinity to kind of disperse laterally than it does for it to capture CO2. So you're never going to have the CO2 capture like right where you added the stuff. So I guess I'm wondering what y'all's views are on if you're going to be doing some kind of measurement, reporting, and verification, what actually does need to be directly observed and what inevitably will need to be modeled.
Well, maybe I'll just set the stage in terms of like helping people understand what is the current mental paradigm for doing MRV with an OAE, and then you can kind of jump in about the spaces. So if you think about this process, and again, just acknowledging that the reality is that the actual carbon removal will not take place local to the activity. Some of it may, and that depends a lot on the oceanographic conditions and the location, but a significant portion of it is very likely to happen out into the open ocean in a place where it can't be observed. We don't actually have the networks to observe it in that space, and the signals are so small relative to the natural background and the background variability. And so we typically think about these zones that exist within something like a coastal deployment. So one is this area which we would call like the zone that's right at the location of a dispersal, right? So this could be if you have an outfall in a coastal environment, there's just within tens of meters around that, you actually have a hope in that space of actually being able to do direct measurements of changes in pH or alkalinity, or even take CO2 measurements in those areas. These are these concentrated zones where we expect, if there were any sort of very acute impacts on biological systems, maybe you would see them in those areas, right? But again, these are very, very small areas. The next zone we have is called the mixing zone. The mixing zone is about maybe up to 300 meters or so around there. This is a kind of a concept that comes out of water quality. This is the area which we expect that any signals that we put in would dilute and mix back to the background ambient, right? So by definition, we don't expect to be able to take any measurements beyond the mixing zone. That's why a mixing zone is defined in that way. And so beyond that area, what we're really talking about when we're talking about doing the MRV is moving into a space where we have to start to use modeling systems to actually track and make predictions about where that alkalinity moves and where the carbon dioxide removal takes place. So I think when you're talking to folks, I will turn it over to Anna, is she will be talking really more about like what's happening quite locally that you can actually measure with direct sensors.
Yeah, so I completely agree with what Alicia just said. We can make measurements of things like pH. We can get water samples to do dissolved in organic carbon. We can do PCO2 directly. But we can only do these for a certain amount of time if there's a short dispersal, because the signals, as Alicia said, are really, really small compared to the background levels. I think one of the things we want to think about kind of going looking long term are what are the parameters that we want to measure, because we can measure quite a lot of different parameters either directly or by taking water samples, but maybe we don't need to do them all. Maybe we can choose a few that will give us the data we want, which will then feed into the models that can do like the longer term casting. But right now, like I said earlier, is like we took every kind of measurement you could possibly take. But I think if we could focus that down onto a smaller subset for the immediate measurements, and then shift over to the modeling.
So maybe just jump in with one point, and that is that I think the measurements that we're going to make are going to change dramatically over time. And as we move to scale, so I think one of the things that we should be thinking, a thing to have debate in avenues like this is, as we have the first kind of at-scale ocean alkalinity enhancements that are funded by market activity, how much do we want to learn how much do we use those as a tool for learning versus how much do we want to rely on funding that is more academic studies and targeted at specific questions. And if we realistically, we do have a finite amount of money that can go into learning about this practice as soon as possible. So I think it's a debate of where we put that to eventually be able to move to a system where the amount of measurements are relatively limited and it's focusing on the actual practice. The money going into it moves from learning into actual driving a climate impact. And and I think everybody in this room, I'm sure, has a different view of how we make that transition.
Okay, so I'm going to ask one more follow-up question, and then I do want to open it up to the audience in case anybody has a question or two, too. So I guess just to jump into that further a bit then. So how does MRV look at the gigaton scale? What does it actually look like, both from a modeling and observation side? What does an observational network need to get right to be credible, and what does a model need to be right to be credible in that context?
Okay, let me take a stab because it's a little spicy, like what it looks like.
There we go.
And just to give everyone context who is not directly in the OAE space, so there is what would be described as something that actually sounds kind of clean. Like we take observations here and we pass them off to models. And I think as scientists, this makes perfect sense to us to have this process for doing the full quantification. That is not without a lot of consternation, actually, in terms of people who are just outside of the I would say the direct scientific sphere. And a big part of that consternation is around, are the models good enough, right? I showed you a simulation. I can tell you why you should believe it, right? But those descriptions may or may not land with you as meaningful depending on your background. And there is a general distrust for modeling systems, especially ones that become more and more complex. And these are very complex modeling systems. And so this question of whether or not models are adequate for doing the MRV and the quantification is one that is very alive right now within the ocean carbon dioxide removal space, and actually within all of open systems. So this is not just for oceans. It's also true for ERW. It's also true, likely actually, for forestry, right? Those models are used all the time for these types of things. And so I think that there's a knee-jerk, I would say, and maybe not unhealthy reaction right now of people making these questions over and over again. Why should we trust these models? Why should we trust these models? And we have a long-term practice within the oceanographic community of validating models. Like this is, if you've gone through a graduate program in oceanography, you've probably thought about validating models. And what ends up happening is we talk a lot to people about how we validated these models against existing observing systems. These are not existing observing systems of OAE. These are existing observing systems of temperature, salinity, current structures, things that are basically helping us have faith in some of these background processes that are within these modeling systems. Those arguments that we make about that, they are very much dependent on having what we call the backbone observing network of the ocean. So we know we're going to talk about, and you're talking about these direct measurements of OAE, but really to understand whether or not our modeling systems are working for this problem and tuning them to work for this problem is one of maintaining these background global monitoring systems that are done not by companies and not by individual industries, but by whole governments and by collections of governments and scientists over decades. Okay, so there's an important role when we think about even this question of do we trust models, of thinking about when we say do we trust them, what are we comparing them to? And the answer is these backbone observing systems within the ocean.
Great. Yeah, I can go next. I think what I would say from that is if it's something is truly at gigaton scale, it has massive government involvement. So it's going to look a lot like how NDCs or how missions reporting looks, which is variable by country and constantly evolving and a little bit flawed, but also gives us a pretty accurate picture of what's going on.
So I think the MRV is also going to depend on where we're doing the dispersals. So if we're working in the coastal environment versus the open ocean, it's very different. So if we're working in coastal environments, we can we could put lots of different instruments out there. It's much easier to make those measurements. If we're working in the open ocean, then we have this bit of a harder challenge. And so what we have to do is either look for technologies we can leave out there, such as like buoys, or we, in the oceanographic community, we now have autonomous surface vehicles, for example, where we could put instruments out there. They could make measurements after it's happening. And so I think we need to think about where we're going to do it and adapt what we want to do based on those environments.
Yeah.
So I'm just to add on to this, which is something that's not about science, but more about the way we envision what could come into being in terms of people getting, I would say, comfortable with these sort of open systems quantification. Is, one of the things that we have observed is that these modeling systems, which I showed you simulations of, they're actually quite expensive to run, both from a computational perspective, also from a personnel perspective. Right? You actually need very specialized people to be able to run these types of models. So it's not an inexpensive endeavor. Similarly, with taking observations in the ocean, obviously that's even more expensive. And so I think we think a lot about this question of whether or not we really want a future world where individual companies are having to calibrate and run these models at a global scale on their own, or whether or not we want to have sort of a common, MCDR utility that allows people to use, for example, like basic understanding of some of these underlying simulations, but then exist as sort of factors of efficiency that they can then apply. And so this is about sort of the separation of concerns that I think is very alive right now within the community, which is what is the responsibility in terms of the MRV of the individual company, and what is the responsibility of the broader community of researchers and eventually, we hope, governments in creating some of these background, I would say, data sets or assets that allow there to be more kind of a normative understanding of, okay, we know if we add this much alkalinity in this location, we expect there to be ultimately this much uptake within X number of years with this uncertainty bound, right? That's something that can exist as a standardized type of understanding within a community that they can be codified within registries and things like that. So I think we have to look beyond like just what's happening right now, but as we move into scale, we have to start to think about this standardization of some of these practices as well.
Great, thanks. I do want to open it up to the audience in case people have a couple questions. Ken?
I play an advisory role with an organization called contrails.org.
And so my question is there any sort of communication between the ocean alkalinity edition communities and other open kind of communities to get a broader acceptance of this idea of verifying actions but trusting the models for amounts?
Well, yeah, I think great question. And I think part of it is going to be a question of the scale and where we are. Like, I think one of the things that's will be interesting to see that is the most obvious kind of area of that's playing out right now is in the current UN or the current IPCC groups that are convened right now. Unfortunately, will not be discussing ocean alkalinity enhancement from mineral addition, but will be discussing alkalinity enhancement and coming up with both, or potentially coming up with both the tier 1 and tier 3 for alkalinity generation from coastal restoration. So for ocean alkalinity enhancement, that's kind of the closest analogy where you have a practice that would be well documented, and then that can tie into a tier 1 crediting. And mangrove restoration, for instance, is already has an emissions factor, basically that is a model dependent, or it could be something that's an empirical calibration from that. So I think, unfortunately, that we missed out an opportunity with the current IPCC authors to be able to do that for alkalinity enhancement is something that is a lost opportunity. It means we're gonna have to wait quite a few years to move back on that, and something that, as a community, I think we should reflect on as how exactly that happened and what can we learn from that.
Yeah, I'll just add something to that. So I think that this, just to in the spirit of your question, which the way I take the spirit of your question is something like there is a universal problem, which is for many systems we have to rely, especially open systems, we have to rely on models. And what is the mechanism by which we develop trust in those models, right? And that I think transcends obviously our problem here. And, we basically, I'll just tell you kind of the story of how we've been thinking about this, is that we were looking actually towards the RW community, which with an observation that they actually have quite intensive modeling practices that they have to do. But there has tended, at least from the outside, that my observation is that there's been a bit less scrutiny than there has been in the ocean. That may be changing, and other people can weigh in on whether they think that's still true. Um, and so that may not be the best example, actually, right now. Within carbon removal might be the next, but not best example. And so what we've been thinking about is looking outside, really, of our carbon dioxide removal space and what other industries and practices are actually very model reliant. Um, and there actually tends to be kind of a relatively robust list. And I'll give you just a few that came up and how they actually transpire in practice. We'll see how we can use those. But like, for example, in things like aviation safety, people use computational fluid dynamics models all the time as part of their design principles. Those are fundamentally the same equations that we're dealing with here. Also, same with contrails, maybe just minus the chemistry. And there are whole practices and standards around safety in those types of industries where people come to terms with the fact that they are using models of a physical system, but that they need those models to make actually very, very high stakes decision making. So that's one example. There are models that I'm less familiar with in things like pharmaceuticals, which are used in order to do sort of stage gate early trials. That happens in pharmaceuticals as well. We see that these types of models that are similar to these are used all the time in decision making around water quality decisions. People have to, again, come to terms with the pluses and minuses of them and make high stakes decisions as a result of them. And so I think there's a whole collection of these types of examples that it would be great to collaborate on, sort of pulling together examples of, and relevant to the SRM field too, areas where we as a community and a society have to come to terms with the use of modeling systems. It's very much part of the current AI debate right now. How do we come to terms with those types of models as well and use them in a trustworthy way? So I think there's examples out there that we can learn from.
So one other just quick follow-up on that, Ken, is that I think one of the things that it really depends on the context, but some of the things that we need to do a better job on when we talk about model uncertainty is how much realistic uncertainty is there. Some of that can come from model and comparison projects. If you're adding slaked lime to a setting, there may be 15% uncertainty in the amount of carbon dioxide removal you estimate you have, but maybe that doesn't matter. It really depends on the context of what we're doing it for. And I think we move too much into, because these are decisions that will have a big impact. I think we move too much into the sense of worrying about uncertainty without placing that in the appropriate context.
I just want to add too, in terms of how uncertainty plays into policy decisions around additionality. There are a number of policy levers in a bunch of other contexts where you have to deal with uncertainty and additionality when you make decisions. Social housing is a good example. So Adam, who's back there, is working on how this particular problem maps into carbon credits. But there's a lot of ways that you can deal with this issue where there's already examples out there in reality. Any other question? Yeah?
The oceans aren't static. They're not a climate system that will be the same in a decade as they are today. And, there's any number of changes, marine heat waves and toxins and pollution and coral reefs collapsing, and we could go on and on and on. What does the science say? How are you approaching the fact that what you're doing today and its impact and results may or may not be applicable as the ocean is a different ocean in 10 years or 20 years?
I can take a first go at that. I think one of the things of why we want to have a combination of mechanistic models and things that are more empirical calibrations is that the oceans are ever changing. Luckily, chemistry and physics are not. So we can be certain that kinetics and basic reactions are going to behave the same way, and we will still, without question, despite where we go, have some basic monitoring that allows us to tie into things. And I think that also goes back to again, what level of uncertainty do we feel comfortable with? Does that introduce a 5% uncertainty in some regions, or does it add something that's, a 50% uncertainty? So it's really regional specific, but reliance on the fact that chemistry is going to do chemistry is I think an important grounding thing that we need to keep in mind, despite that oceans are complicated.
So, I mean, I think it's a great question, and I think the reminder there, which is consistent with what Noah said, is that the the it's actually very hard to answer those questions. It's not easy, but we do have tools in our arsenal to start to chip away at them. That's the really good news here, and the reason why these models actually are so powerful is exactly this, is that they are based on some fundamental equations in chemistry and physics. I think the biology is a little less fundamental, right? There's work that needs to be done there. But they can be used in the sense of trying to actually probe some of these levers of uncertainty. And the way that we do that is a very simple way, really, which is to run ensembles of model simulations out into the future. That's the very basic tool that we have in our arsenal as scientists, is we can take these modeling simulations and we can make changes in terms of, okay, let's imagine we do have more marine heat waves. Like, what is that going to do to the uptake efficiency? We can ask those questions. And so when I say it's not easy, what I mean is every question you want to ask then requires like a 2-year postdoc to like think about that and run those experiments. But they are tractable problems. We have the tools to start to chip away at those levels of uncertainty because we have invested as a society in decades of work building out these complex computational models, and validating against a baseline observing systems.
I think it's also worth noting, the ocean is ever changing, but the ocean also changes very slowly. It's a sluggish system. It's sort of what keeps the timescale of evolution of the climate system at all itself slow. And so it's not like 10 years from now we're going to have a radically different ocean system that we can still that's what keeps the uncertainty about the future potentially low, and when we ask these questions, and not it's not like the atmosphere in that way. I think maybe one more question from the audience. Gabby?
Hopefully this will be a good question to end on, since it's a little higher level. Thinking about the name of this panel, scientific constraints of what works for OAE in the real world, right? Listening to the panel here, we certainly talked about science, but we've also talked a lot about different social considerations and things like that. So I would love to hear from each one of you if you really feel like it's the scientific constraints or the social constraints that are preventing OAE from maybe moving forward in the real world. And social constraints can certainly be, policy, public acceptance, but also just the information exchange among the scientific community.
Can I have a different answer? Can we talk about funding? I mean, I think that, what we did is we did a trial and we engaged the community, and we kind of did all of that encompassing, but on a small scale. But I think to move forward, we have to figure out how to get funding to do more experiments, to do more modeling, to engage more communities. And so I think we have to think about, where is that funding going to come from? And right now, funding is hard for science. And so thinking about that, and I think all of the things you mentioned are really important for moving forward.
Yeah, I mean, I definitely think it comes down to the social and political constraints and how those map onto funding constraints. And I think of that as all sort of one piece there. And I think that, but the important thing to keep in mind is the chicken and egg problem, right? It's obviously, as we move through this space of actually loosening some of those constraints and having more fluency on the policy and the social level, I think that is going to unlock more funding, right? So I think that there's a thing. But then the other thing to observe that I've seen is that the more research that we have right now, that in and of itself then unlocks the ability to have more social acceptance, right? And so one of the really promising, I would say, trends that we've seen within the OAE space is this huge explosion of research, new research, and people coming into the research field, a lot of times earlier career or mid-career people coming in to the research space. And that is just driving this enormous amount of new literature that's coming out. And that literature is able to then form the scientific basis for things like the CRCF or an IPCC process, et cetera. And so I do think there is this sort of laddering and bootstrapping that's happening between the science community, the funding that's needed, and then sort of the broad social, I'll say not even just acceptance, but fluency in like, what are we really talking about here when we talk about things like ocean alkalinity enhancement?
My response would be very similar to that. Is the way I often think about it is we need to have the science in place to be able to take advantage of opportunities when they come. Ultimately, it's going to be money that has to drive these processes. So if you can take advantage of funding opportunities when they come up with having the science and the tools available, I think that's the right now over the next decades is going to be what's essential. And I think as an example from that, to end on talking about wastewater, which is a responsible thing to do right before we break for lunch here, is that it's having basically tools to think about how alkalinity generating minerals will behave in wastewater treatment plants and what would be the fate of the alkalinity as it leaves wastewater treatment plants, allows us to be able to tap into plants that are having troubles with meeting their permit requirements because they have inefficient microbial processes. So it's a case of we need the science to be there to take advantage of cases where there's going to be money that can fund processes that drive us to positive change.
Are we going to end?
I'm going to ask one last question, but you
Okay,
can.
but I want to say,
Yeah.
so I want to make a big, I don't want to lose, I want to just remind everyone, because I think it actually is important for the SRM field too, to kind of hear this reflection a little bit, is that we have seen really a transformation happen within our understanding of OAE and what are the important things to think about in the last couple of years, precisely because of field trials in water field trials, like we've talked about here with Loch Ness. And the ways that we were talking as a scientific community and as a policy community 5 years ago were very high level, right? And an example is like we were looking at modeling simulations like I was showing you, and those are very revealing in many ways, right? But that the huge transformation that has happened is because we've had commercial companies do pilots, and we've had research organizations do pilots, and I think there's been 4 or 5 now pilots globally. And what they have brought into the fore is this whole host of interesting issues about the connections between our understanding of the science and the deployment strategy and how married those two things really are. We've learned a lot about the deep heterogeneity within the ocean and the deployment systems that we chose. We are understanding more about which processes are really important in that near field zone where deployment will actually happen. We're understanding more about some of the constraints. We're understanding more about community engagement, right? So I think it's hard to overstate the value of doing real world deployments in order to drive the science and also start to drive things like the pressure on the regulatory environment to sort of step up and develop their own fluency and their own ways of understanding the way that the regulation can happen.
Great. Thanks. I'm going to ask one lightning round question. I'm going to blatantly rip off a question from a self-described clueless economist from yesterday. What will be the first year with a gigaton of durable CDR?
2040.
2050.
Oh, I don't know. I'm hoping it's sooner. I'm going to go with 2030.
Scientific optimism right there. Thanks, everybody.